Well, howdy there, geometry travelers. I hope you're having a good day, and then a little bit of geometry won't ruin it for you. Here's your latest geometry video. Why don't you take a moment, pause this video, and list 3 examples of objects that change their size. 3 objects that change size. All right, did you think of 3? Let's see, here's one that I thought of. A balloon. When you blow air into a balloon, it gets bigger, and when you let the air go, it gets smaller, and so you can make a balloon change size. Here's another thing. I think this is right. When you go in and out of the light, if it's lighter outside and you're out there, your eye iris is smaller, the hole. I don't think that's the actual iris. What is that called? Anyway, you get the idea. The hole in your eye that the light goes through gets smaller when it's bright outside, and then when you come inside when it's dark, it needs a moment to like adjust and open back up again so it get more light in. And so the eye iris is something that can change size. Can you think of a third thing? How about puppies? When they turn into dogs, they change size, they grow, they get bigger. So it is just about every living thing, by the way. Flowers, bunnies, people, all of us change size. So changing size is a super important thing to look at because so many things change size. Today, that's what we're going to be looking at in terms of geometry. But before we do that, you're going to update your notebook. In some right-hand column, somewhere in your notebook, write yourself some questions on a page that you haven't done that yet. Find another page where you need to write a summary. Remember that summary is going to be the answer to the essential question on that page. And then do what you got to do to get a new page started. You can go ahead and pause and do that. All right, so here's your new set of notes on a new note page. Start at the top with your topic, dilations with positive scale factors. Your essential question right underneath that topic should say, how do you dilate a figure with a positive scale factor? That's the question you should be able to answer at the end of this video, or maybe when you finish the assignment. If you can't answer the essential question, come to office hours. Ask me, I can help you. All right. Oh, also, don't forget to put that topic in your table of contents and the page number that you're about to take notes on. All right, so far for a little while now, we've been talking in your geometry class about transformations, the ways that things move. We started out with translations, and then we went into reflections, and then we started talking about rotations. All 3 of those transformations, nothing changed size. They moved in one way or another from one place to another. But what they didn't do was change size. And of course, things change size. So this is our 4th and final transformation called dilations. This is where we start talking about how things change size and the mathematical and geometric ways that those things happen. So what is a dilation? Well, a dilation is a transformation where an object, sorry about the feedback, changes size. When something changes size, it has to be measured. We have to know how much it changed size. And so we have to have a starting point for that. And the starting point for a dilation is called the center of dilation. That's where we're going to be measuring our dilation from. So the center of dilation is a point from which a dilation is measured. The measurement itself has a particular name. It's called a scale factor. This scale factor is going to be a number. And when we don't know the number, it usually is indicated with the letter K. Just like a lot of algebra problems has, you're solving for x. With scale factors, generally, we use the letter K for that. The scale factor is the measure of the size of the dilation. There's some key points when it comes to dilation, and I'm just going to write them, and then we'll talk about them. First thing is that angle measures are preserved. And the other thing is that side lengths change. This is kind of the bottom line of how things dilate. So when we say angle measures are preserved, what we mean is that if you take a look at this object right here, we have a pre-image, triangle PQR, and an image, triangle PQR prime. The angle PRQ, this one, will have the exact same measure as angle PRQ prime. Those two angles will be congruent to one another. Same thing is true for RPQ and RPQ prime. They will be congruent to one another. Those angle measures are preserved throughout that dilation. And so PQR has the same measure of PQR prime. Angle measures are preserved. From the beginning of a dilation all the way through, those angle measures will remain congruent from image to from pre-image to image. So how do things dilate? How do they change size? It's because their sides change. The side lengths will not be the same. Now going from PR to PR prime, you can see that that side length got longer. Same thing with PQ and PQ prime and RQ and RQ prime. Those side lengths, those segments have different measurements. That's how we know that we have a dilation. If the angle measures are the same and the side lengths have changed, that's a dilation. You can calculate a scale factor by using a little formula. And I'm going to write this out a little differently here. Let's talk about what CP prime is. CP prime is a distance, and specifically it's the distance between the center of dilation, C, and a point on the image. That's the distance between those two things, CP prime. The distance between the center of dilation and the image. Remember, the image is the object after it has transformed. All of that gets put over what's called CP. CP is also a distance. It's the distance between the center of dilation, again, C in this case, and a point on the pre-image. So CP is the distance between the center of dilation and the pre-image. So if you know those two distances, you can stack them up in a little division problem and you can calculate the scale factor K. So in this particular example, K is going to equal CP prime, which is the distance between C and P prime, which is 6. And the distance between C and P, or CP, that is 2. And then you can divide 6 divided by 2 to get 3. And that means that the scale factor of this dilation is 3. We can calculate it that way. What that scale factor means is that triangle PQR, sorry, let me say it this way. Triangle PQR prime is 3 times bigger than PQR. And that's where we get that language. When someone says this thing is twice as big as this other thing, what they're talking about is a scale factor. It's 2 times bigger. The scale factor is 2. In this case, it's 3 times bigger. The scale factor is 3. And we can calculate that using that tiny little formula. All right, before we get into examples, let's do just a little bit more understanding. So dilations come with two types. It's common to think that a dilation is always something getting bigger, but that's not always the case. In math, a dilation can get bigger or smaller. We still call it a dilation. When a dilation gets bigger, it's called an enlargement. And when a dilation gets smaller, it's called a reduction, which makes sense. So an enlargement is a dilation where an object gets bigger. And then a reduction is a dilation where an object gets smaller. And that's not really a surprise. We know what enlargement means, we know what reduction means, and so that kind of follows along. But the one thing you want to think about is that you can calculate a scale factor, and you can tell whether it's going to be an enlargement or a reduction just by knowing the scale factor. So something is going to get bigger if your scale factor is bigger than 1. So think about that example that we had back here. Notice that triangle PQR prime is 3 times bigger than PQR. The triangle has gotten bigger by a scale factor of 3. Notice that 3 is bigger than 1, and so this follows along with what we're thinking about. Anytime you have a scale factor bigger than 1, you have an enlargement. Things will get bigger. Now, reductions look a little bit different, and I'm going to write it and then we'll talk about it. What that little phrase is telling us is that our scale factor, k, is somewhere between 0 and 1. It's not going to be exactly 0 because it might not exist. And it's not going to be exactly 1 because then it wouldn't change size at all. It would stay exactly the same. But something will get small if your scale factor is somewhere between 0 and 1. So what kinds of numbers are between 0 and 1? Well, there's a number between 0 and 1. There's another one. There's another one. Anytime you have a number where it's a fraction and the number on top is smaller than the number on the bottom, that is a number somewhere between 0 and 1, when there's a 1 on the top. Anyway, if your scale factor lies somewhere between 0 and 1, that object will get smaller. So let's do a couple so I can be a little bit more clear about what I'm trying to tell you. So here in A and B, we've got a couple of objects. We see that there is a size difference between them, and we want to figure out their scale factor. So the first thing to do is find the scale factor of the dilation, and then tell whether the dilation is a reduction. In other words, the scale factor is between 0 and 1, or an enlargement because that scale factor is bigger than 1. So just looking at A, we have these 2 safety pins. We want to be able to calculate our scale factor. And so we know that K is going to be the distance between C and P prime. And we're going to divide that by the distance between C and P. So what's the distance between C and P prime on this object? Well, it looks like it's 12. And we're going to put that over the distance between C and P, which is indicated to be 8. Now, because 12 is bigger than 8, we already know that this is going to be an enlargement, and we can kind of see this from the figure as well. But you won't always be able to see the figure, and so being able to calculate is a really good idea. Let's see, let's reduce 12 over 8. So we would have, let's see, 3 halves, which is about the same as 1.5, isn't it? So notice that that number is bigger than 1. 1.5 is bigger than 1, and so we can comfortably say that this is an enlargement. So here's our scale factor that we calculated, and here is what type of dilation it is. Now looking at B, I bet we can guess that it's going to be a reduction, but let's calculate it and see. So let's see, the distance between the distance between C and P prime in this case is 18. See that? CP prime. And then the distance from C to P, way out here, is 30. And so we have 18 divided by 30, and you know, you can just plug this into a calculator if you want to. We could say, we'll turn your calculator on, Miss Waite, 18 divided by 30. Now notice that that top number is smaller than the bottom number. So this is a number between 0 and 1 if we just know about that. But when we plug it into a calculator, 18 divided by 30, enter, what we get is 0.6. This is the same as 6/10. This is a number somewhere between 0 and 1, and so this is a reduction. Anytime you calculate your scale factor and you get a number between 0 and 1, it's a reduction. These objects get smaller. All right, so here's an example where we do not have the figure, and so we're going to have to calculate the scale factor and then tell whether the dilation is a reduction or an enlargement based on what we found. So it says, in a dilation, CP prime equals 3 and CP equals 12, find the scale factor, then tell whether it's a reduction or an enlargement. And here's our little helping formula. So we want CP prime on top. Well, CP prime is 3, and CP is 12, and so 3 12s would reduce down to 1/4, and that is a number between 0 and 1, and so we know it's a reduction. We calculated the scale factor K, I should say K equals here, and we found that it was a number between 0 and 1, and so we know it's a reduction. Okay, so that's how you calculate scale factor and you tell whether or not something is an enlargement or a reduction. But that's sort of general stuff. Now let's think about it in terms of geometry. Just like with reflections, just like with rotations, there's rules involved. And it turns out that for dilations, there's one rule, and it looks like this. For every xy point, you're going to change it by the scale factor. So if you have a point, all you need to do is take each x and y value and multiply it by the scale factor to get your dilated new point. So let me show you what I mean in an example. Example says ABC has vertices A, B, and C. Find its image coordinates after a dilation with a scale factor of 2. And so we can use this coordinate rule because we know that A lives at 2, 1. There it is in the problem. A is at 2, 1. And we want to change it using the scale factor 2. And so what we can do is we can just multiply this 2 and this 1 by the scale factor and get A prime. So A prime is going to be 2 times 2, which is 4, and then 1 times 2, which is 2. And there's where A prime lives. You just take each number in that point and multiply it by the scale factor. B lives at 4, 1, and so B prime must live at 4 times 2, or 8, and then 1 times 2, 2. And then the last one, C, lives at 4, negative 1, and so C prime must live at 4 times 2, or 8, and negative 1 times 2, or negative 2. And these new points are what you would graph in order to see your new dilated triangle. Now, since it has a scale factor of 2, and this isn't asked in the example, but is that an enlargement or a reduction? If you said enlargement, you're right, because 2 is bigger than 1. And every time you have a scale factor bigger than 1, you have an enlargement. All right, so let's see this on a graph. We're going to graph a quadrilateral. I already have it done for you with vertices K, L, M, and N. And we're going to now graph its image after a dilation with a scale factor of 3. And so we have to calculate those new points using the rule. Remember, the rule says take every point x and y and change it so that you're multiplying the x by the scale factor and the y by the scale factor, and that's going to give you your new points. Well, let's see. K, we're told, lives at -1, 2. So we're going to calculate K prime by running it through that rule. Well, let's see. We have a scale factor of 3 this time, and so we're going to multiply -1 times 3 and get -3, and then 2 times 3 and get 6, and now we have a new point that we can drop on our graph. -3, -1, 2, 3, +6, +1, 2, 3, 4, 5, 6, and this is K prime. Now we can calculate L, which lives at 0, 2. And we can find L prime by running it through the rule. What is 0 times 3? It's 0. What is 2 times 3? 6. You just take each of these values, multiply it by the scale factor, and you get your new point. So our new point, L prime, lives at 0, +6. So 0, 1, 2, 3, 4, 5, 6. Here is L prime. All right, let's see. What happens with M? It originates at 1, 1, and we want to find M prime by multiplying by the scale factor. Well, 3 times 1 is 3, and 3 times 1 is 3. And so we have a new point we can graph, 3, 1, 2, 3. There it is, and here's M prime, and we have 1 to go. N, which starts at -1, 1, and goes to N prime, which is going to be found by calculating 3 times -1, which is -3, and then 3 times 1, which is 3, and we have a new point, N prime, that lives at -3, 1, 2, 3, +3, 1, 2, 3, N prime. And now when we connect our dots, we see that we have a new object, KLMN prime, that is 3 times bigger than our original object. Now, here's something to think about. It might have seemed like that object also translated, but remember how dilations work. They get measured from a center of rotation, center of dilation, which is a point. And when you're graphing objects, that point is going to be the origin. And so what you have here is a dilation that comes from the origin. And it can connect all of those points together. So the distance between the origin and N, and the distance between the origin and N prime will be 3 times. That's how these things go. And so they look like they move, but they really are just growing with the center of dilation being the origin. So it kind of makes it look like it moves away as well, but it hasn't. It's just dilated. It does what dilations do. All right, friends, so that's about it for today. The topic was dilations with positive scale factors. The essential question, how do you dilate a figure with a positive scale factor, should be answerable right about now, but if not, then do a little bit more work or talk to me during office hours and we can clear things up. Here is your practice. On Google Classroom, I have dropped a piece of graph paper for you. I'm going to ask you to plot a quadrilateral on it, anywhere you want. Put a quadrilateral down on that piece of graph paper. Then choose 2 different scale factors. Maybe one is bigger than 1 and one is somewhere between 0 and 1. It's totally up to you. 2 different scale factors. And then dilate the quadrilateral by those scale factors. So by the time you're done, you should have 3 objects on your paper. And then this says upload your new graphic, what I meant was graph, typo, to Google Classroom. And however you do that, take a picture of that piece of graph paper when you're done and upload that to Google Classroom, or you know, however you can work it out would be fine with me. All right, you guys. Well, it's been lovely, and I hope that your evening goes well, or your, I don't know, it's evening right now for me, so whatever time it is, I hope that whatever's happening next is fun. You guys are awesome. Thanks for working so hard. Talk to you later. Bye.